All right, let's talk about something that's literally all around us, but most of the time we don't even see it. I'm talking about fluid dynamics. From the water in our pipes to the air holding up an airplane, understanding how fluids move and behave is absolutely core to what we do as engineers. So today, we're going to open up the toolkit and demystify this whole subject.
So here's the big question, right? How on earth do you even begin to model something as wild and chaotic as flowing water or air? I mean, it just seems impossibly complex. Well, the key, like with so many things in engineering, is to start with the basics and then build our way up.
So, here's our game plan for today. We're going to start in the beautifully simple world of the perfect model with ideal flow. Then, reality's going to bite when we get into pipe flow and see what happens when friction joins the party. After that, we'll unleash the flow in open channels where gravity runs the show. And we'll wrap it all up by shaping the world with drag and lift, the forces that literally let us take to the skies.
Let's kick things off with a concept that, I'll admit, might sound a little weird at first: the ideal fluid. And I know what you're thinking. Why would we start with something that doesn't actually exist in the real world? Well, think of it like learning to ride a bike with training wheels. You start with a simplified model to nail down the basics before you have to deal with all the complexities of the real thing.
So what exactly is this ideal fluid? Well, just imagine a fluid with zero stickiness, no internal friction, no viscosity at all. It's like water that flows without any resistance whatsoever. By making this one big assumption, we get to strip away a ton of mathematical complexity and just focus on the absolute fundamentals of how fluids behave.
And this simplified approach is awesome because it unlocks a really powerful tool for us called Euler's equations. The easiest way to think about them is that they're basically Newton's second law, force equals mass times acceleration, but specifically tailored for our perfect frictionless fluid. They really are the foundation of this ideal model.
And here they are. Now, don't let the math on the screen throw you off. The real takeaway here isn't the symbols, it's the concept. What you're looking at is this beautiful dance between two main forces, the push and pull of pressure and the fluid's own inertia, its resistance to changing motion. In our ideal world, it's a perfect, elegant balance.
And this is where it gets really cool. Even with this super simplified model, we can predict some incredibly complex and honestly, really beautiful flow patterns. This whole approach is called potential flow theory, and it's a fantastic tool that gives us a powerful starting point for understanding how fluids really move.
I mean, just look at this intricate pattern on your screen. It's called a doublet, and it looks crazy complicated, right? But what's totally mind-blowing is that we can describe it perfectly with this simple math of ideal fluid theory. It's just an amazing testament to the power of starting with a simplified model.
All right, we've had our fun in the perfect, clean world of ideal fluids. Now it's time for reality check. Let's step into the messy, complicated, but fascinating world of real fluids, where friction is a force you absolutely have to reckon with. We'll start by looking at what happens when we confine a fluid inside a pipe.
You see, in the real world, fluids and pipes have a split personality. At low speeds, you get this beautiful, orderly laminar flow, where the fluid moves in these smooth, parallel layers. But as you start to crank up the speed, things get wild. The flow becomes turbulent, a chaotic, swirling mess of eddies that just drains a whole lot more energy from the system.
So how do we engineers actually predict this energy loss? We use a legendary tool that every engineer knows and loves, the Moody diagram. This thing is a masterpiece. It connects three crucial pieces of the puzzle: the Reynolds number, which tells us if the flow is calm or chaotic, the relative roughness, which is just how bumpy the inside of the pipe is, and the friction factor, which is our key to calculating the energy loss.
But wait, there's more. Pipes are never just straight lines, right? They've got bends, valves, inlets, and all sorts of other components that disrupt the flow. Each one of those fittings acts like a little speed bump, causing the fluid to lose energy. And to account for that, we use a handy little number called a loss factor.
We've seen what happens when we drop a fluid in a pipe. Now, let's take the top off and see what happens when we let it run free. Welcome to the world of open channels. Think rivers, canals, and spillways, where gravity is the undisputed boss.
To get a handle on open channels, we have to talk about specific energy. It's a simple but really powerful concept. All it is the total energy of the water at any given point. And it's a combination of two things: its potential energy, which comes from its depth, and its kinetic energy, which is all about how fast it's moving.
And just like in pipes, open channel flow has its own two modes. You can have calm, tranquil flow, where the water is deep and moving slow, Or you can have wild, rapid flow, where it's shallow and moving fast. The switch that tells us which state we're in is called the Froude number, a clever little value that compares the speed of the water to the speed of a wave.
Now, this is where things get really exciting. When that fast-moving, rapid flow has to slow down, it doesn't do it gracefully, it does it with a bang. It's called a hydraulic jump, a sudden, violent transition to tranquil flow that releases a massive amount of energy all at once.
To really get your head around a hydraulic jump, this analogy is perfect. Think of it like a shockwave from a supersonic jet. In both cases, you have this sudden, dramatic shift from a high-energy state to a lower-energy one, and they both release a ton of energy in the process. It's a powerful reminder that these principles of fluid dynamics are universal. Okay, we've looked at fluids inside pipes and flowing freely in channels. For our grand finale, let's zoom out and look at what happens when an object moves through a fluid. This is where we run into two of the most important forces in all of engineering: drag and lift.
Now, drag isn't as simple as it sounds. It actually has two faces. First, there's friction drag. This is caused by the fluid's viscosity literally rubbing against the object's surface. It's the main player for sleek, streamlined bodies. Then there's pressure drag, which is all about the pressure difference between the front and back of an object. This is the one that really gets you on blunt, blocky shapes.
And the key to understanding that pressure drag is a little something called flow separation. Imagine the fluid trying to hug the curves of an object. If the shape is too blunt, the fluid just can't stick to it. It separates, creating this chaotic, low-pressure zone behind it, a wake, that basically sucks the object backward.
But it's not all about fighting against forces. We can also use the power of fluids to our advantage. And that, of course, is where lift comes in, the magical force that allows airplanes to fly. By carefully shaping something like a wing or an airfoil, we can create a pressure difference between the top and bottom surfaces, and that difference generates the upward force we call lift.
And there's a beautiful equation that describes this relationship perfectly, the Kutta-Joukowski equation. It basically tells us that the amount of lift you get is a product of three things: how dense the fluid is, how fast you're moving through it, and how much circulation you're creating around the wing. The more of each of those you have, the more lift you get. Simple as that.
So from the elegant simplicity of ideal fluids to the real-world complexities of drag and lift, we've seen how a few of these fundamental principles can help us understand and, more importantly, control the world around us. So the only question is, now that you've got these tools in your kit, which force of fluid dynamics will you harness next? And if you haven't already, get over to our YouTube channel, Mechanical Engineering Made Simple by Strike Vision Studio, where we post hands-on how-to videos, visual breakdowns, and practical engineering walkthroughs you can actually use.